Okay, so welcome back to this seminar. Today is lecture 5 again. And the warm-up part, I just talked to you already, right? So last week we talked about value-based decision-making. We talked about the subjectiveness of value, and we talked about one of the most important brain region, VMPFC, the ventral median prefrontal cortex, okay? And today the topic will be about risky preference and the intertemporal choices, the risky decision making and the intertemporal decision making. And the risky choices, what are risky choices? So as Franklin once said, and in this world nothing can be said to be certain except death and taxes. So here, risky choices, the very important idea behind it is to talk about certainty. So here, certainty. So when something is certain, there is no risk. And when something is uncertain, maybe there is a risk, right? So this is the central idea of risky decision making. So the idea here is risk is linked with uncertainty. So I can show you one of the simple graph here. On the x-axis, so this is the probability. On the y-axis here, it is risk or uncertainty. If there is a probability of 0, basically means it will never happen. It's not possible. So then you know that it never happens. Then there is no risk or there is no uncertainty. You are sure that it's not going to be happening. On the other hand, so here when the probability is 1, you know that there is a 100 chance it will happen for sure. It will for sure be happening. And then there is also no uncertainty. It is sure, right? It happens anyways. So you know that. Then there is no risky or uncertainty. And what happens in between is the risky part or certainty part. And the risk or the uncertainty is the highest when the probability is 0.5. So let's say we have a coin. You want to flip it, toss it, and then you want to catch it. You have no idea what will be the results. It can be a face, it can be a head, it can be a tail, right? But you never know if it is a fair coin. It is 50-50 coin. So this is a high uncertain situation. Okay. So what to bear in mind here is risk is associated with uncertainty. Good. Yes, here is basically what I said again. Risk is uncertainty or reward variance, and it is an inversely quadratic function of probability that is minimal at probability equals 0, probability equals 1, and maximal at probability equals 0.5. Okay. So there is one example, and I can show you how this risk is related to decision making, or how risk is related to value. We talk about value and how value and risk can be related, can be put together. So there is something called a Pascal's wager, and then there's a question asked by him. So the question is, should you believe in God or not? So this is the question, and he gave you a few assumptions. So let's assume that you are uncertain whether the God exists or not. You don't know. So then let's say there is a probability. The probability of God existing is a small number between 0 and 1, okay? And let's assume this probability is not 0. This probability is not 1. It's something between 0 and 1, okay? So this is the probability of God exists. A few other assumptions. If you believe in God and then God exists, then you win it all. So this is the assumption. If the God is really there and you believed in it, then you earn some money, for example. And if you do not believe in God, but God does exist, so then you lose. There are some other scenarios. Let's say if you believe in God, but the God does not exist, nothing changes, okay? Very interesting. Here, if you believe not in God and then the God does not exist, also nothing changes. But this is an unfair game, kind of. So what you do now, what you can calculate, what you could expect is you can actually calculate some expected value. So this is the term. This is the expected value. So what is the value of believing in God? So let's say here, this is the probability that God exists. So if you choose to believe it, then you earn everything. So you win it all. This is nearly like infinity. And then if the God does not exist, but you still believe in it, according to the rule right here, nothing changes. And here it is the expected value of not believing in God. So following the same calculation. So if you look at here, the expected value of believing is positive infinity, and the expected value of not believing is negative infinity. Okay. I saw the questions, and the questions are asking, so why here I say win it all or nothing changes? I don't know. It's quantified by Pascal, so he assumed this way. So this is the assumption. Okay. So it's kind of controversy, I know. So whatever you think about this, the general idea here is that, or at that time, was that you should maximize the expected value. So if Pascal defined all these 4 or 5 assumptions, so here this is also one assumption. So according to this assumption, believing in God has a huge amount of expected value. Not believing in God has a huge amount of negative value, right? So what should people do? So this is basically to convince people to believe in God. So it doesn't matter here. But so here, what he's trying to do is to use some kind of calculation to compute the expected value of something. So regardless of this example, the general formulation is the expected value is a overall summary of the value multiplied with the probability. Okay. So here, if you look at here, the value is infinity, and then this is the probability to get it, and then the expected value is the number, the actual number multiplied with the probability to get it. Okay. But this is maybe a little bit too abstract. What you can do here is to look at here, not here, here. So look at this table. So let's say there is a gamble. There is a gamble. It has 4 outcomes. It has 4 outcomes, 1, 2, 3, 4. So you either get €1 or €2 or €3 or €4. So this is the gamble. You either get 1, 2, 3, or 4. And then here, this table illustrates, this column illustrates the probability to get it. So this is maybe a good gamble. Why? So this is 10% chance to get €1, 30% chance to get €2, 45% chance to get €3, and then 15% chance to get €4. So what is the expected value based on this calculation? What you do is simply you use 1 multiply with 0.1, 2 multiply with 0.3, 3 multiply with 0.45, 4 multiply with 0.15. So what you get is all those numbers, so here, and then you sum it up, okay? Because this means sum, the capital sigma means summary. And then if you sum everything up, you get 2.65. So this is the overall expected value of this gamble, okay? And then if I change the probability of this column, you can calculate the expected value of that gamble, and then you compare which gamble has a higher expected value, and then you can make a choice accordingly, okay? Good. And then in experimental setup, so in laboratory experiments, typical setup can look like this. So in this case, for example, the orange here, the area means the probability. So here it means 100% to win €5, and here it means 75% chance to win €20. And then this experiment asks the participant which one they want to play. Do they want to play the safe option, €5 for sure, granted, or €20 with a relatively higher chance, 70% chance, okay? And if you do the calculation, the expected value of the left gamble, what is that? So it is 3/4 of €20. It is €15. So, okay, so the expected value of this one is €15. It is larger, 3 times as large as the safe option. So maybe a rational decision maker will basically choose this, okay? And this is the same idea. So the area of the chart means the probability. So here 42% versus 58% to win, in this case, 14 some units, and then this one 85 units. Here is the same idea. And then this one is in the literature called mixed gamble. So it is a 50% chance. So here is the chart. Here, this is a circle, and there's a line here. It basically means 50%, half of the chance to win $6, and here half of the chance to win to lose $18. This is why it is called a mixed gamble, because it mixes the win, the gain, and also the loss. You will see also later in the presentation. Okay, good. And then if you calculate, 50% of $6 is 3, right? And then this one, 50% chance of minus $18 is minus 9. And then you use 3 minus 9, you get minus 6. So this is the expected value of this gamble. And then you do the same thing in this case, the second case, the expected value is $0. And here, the expected value of the third gamble is positive $6. Okay? So that's it for now. And that is the kind of overall summary of overall introduction of value of risky decision making. And then the second topic of this week is intertemporal choices. And why I talk about intertemporal choice, I can tell you later. But what does it mean to have intertemporal choice? So you also, I guess most of you know this example, right? So if they eat it, they just eat it. But if the children, they wait for some time, so they will have 2 of the marshmallows. So this is a very good example of intertemporal choice. And in real experimental setup in decision making, so how to study intertemporal choices. So most of the time in the lab, we show to participants this kind of decisions. So they can choose from here, this option and this option. The left option means an immediate gain. So you will have 10 euro immediately. I give you 10 euro immediately. And then the second option, it is a delayed option. So I give you 24 euro, but not immediately. I will give you in 14 days, in 2 weeks. And then you make the choice, okay? So why the intertemporal choice can be associated sometimes with risky decision making. So why we group these 2 topics together when we are introducing that in this seminar. So it is because intertemporal choice, also there is some uncertainty involved. So you look at here, this one example. So big goal or something larger money. So let's say if I give you 100 euro in half a year, it is a lot of money, right? 100 euro, but it has some uncertainty in the future. Even though I tell you, you will have 100 euro within half a year, but there might be something going on during the half a year. There's some uncertainty, temporal uncertainty involved. But smaller ones, it is, if I give you 10 euro now, immediately, then it is no uncertainty, no reward variance. So it's similar to a sure option in the risky decision-making task. And then in the literature, researchers are trying to quantify intertemporal choices. They use some mathematical modeling. So throughout this seminar, throughout this course, I talk a lot about computational modeling, because modeling is a very useful tool to approximate what might be happening inside the brain, inside the minds of the participants. So what can be the cognitive process of generating the behavior? So here, the particular model is called hyperbolic discounting. So if you have never heard about it, it doesn't matter. It's basically on the y-axis, this is the expected value. X-axis is the time. So the expected value decreases as a function of time. So if, let's say here, I give you 20 euro. Maybe I can use the same example. I give you 100 euro within half a year. So if I give you the 100 euro immediately, 100 euro actually means 100 euro. But if I give you 100 euro in half a year, so then the value in your mind It's also a little bit subjective. In your mind, decays. So 100 euro in half a year does not mean 100 euro anymore. It might mean something like 35, for example. So then the value is decayed by time. Okay. Good. Any questions? So this is from my part before the presentation. This is a short, but I guess informative introduction of the two topics, risky decision making and intertemporal decision making. Any questions? Yeah, no, good. Okay, if there is no question, so we can start the presentations. Let me just stop the recording.